Okay, so most plate activity is on these edges. And not only is Hawaii one of the exceptions to this, but another exception is over here, and it's called Yellowstone National Park. At Yellowstone, it's a huge volcano. It's so big you don't even realize that you're on a volcano. So Yellowstone in the middle of the North American plate is another exception to the rule. The rule is basically most activity occurs at the edges of plates. So you need a piece of paper and you should label it plate boundaries. You should have some colored pencils ready to draw. I really like this map that I have in the background showing these plate boundaries. First, I just think they did a good job with the colors. They really show the plates very clearly. It includes all the big plates. They didn't split the Pacific plate in half like happens so many times, although they did split the Eurasian plate apart, the purple one. And what else do I like? I like that they have some of the medium-sized plates, the Cocos plate, the Philippine plate, Caribbean plate, and so on. Now, there are many more small fragments of plates too, but these are the main ones. So again, the important thing is what's going on at the boundaries. So let's look at that. All right, now, I do not want you to write all this down. Okay, I do want you to write some things down though. So I'll let you know as we go what you should be writing. So most tectonic events occur at the boundaries between the plates. Tectonic means mountain building or landscape forming, might be a way to define tectonic. Activity that forms a landscape. And these different tectonic events can include earthquakes, volcanic eruptions, and the formation of other landforms like mountain ranges and deep sea trenches. We're going to be talking about all of those over the next 2 days. The way that the plates move next to each other, along with the type of crust involved, really determines what kinds of features and events result. Now, I think I would like to start by having you write down a definition of a plate. So let's write down a definition of a plate. And it's going to be really simple. It's going to be a moving piece of lithosphere. Litho by itself means rock or stone. And so this includes the crust of the earth. It's made of rock and stone. Moving piece of lithosphere. I would also like you to add in parentheses next to lithosphere that it's the crust and the upper mantle. So the lithosphere is more than just the crust. It includes the upper part of the mantle that's carrying the plates along. It's like the upper mantle is kind of like the surface of the lake, and a boat would be the crust. And the surface of the lake is carrying that boat along. And we can consider both the surface of the lake and the boat itself as part of the lithosphere, the upper mantle and crust combined. So what did we write down? Plates are moving pieces of lithosphere, and at the same time, we defined lithosphere as the crust plus the upper mantle. So the way these plates move next to each other, along with the different kind of crust that's involved, determines what kinds of features and events result. So are they moving together? Are they moving apart? Are they sliding past each other? The way they move is important, but also whether it's basalt or granite crust, whether it's ocean floor or a continent. That has a big difference in what kinds of events occur. Of course, the direction the plates move depends on the direction that they're carried along by convection currents in the asthenosphere. And that's why we spent so much time talking about convection currents last chapter. Now, this is a related word to lithosphere. I want you to write that word down, asthenosphere. And it is the next layer down. So it is the lower mantle. Asthenosphere is the lower mantle. This is where the convection currents are found. In fact, that would be really smart if you wrote down lower mantle with convection currents. That'd be great. So I want to remind you that the Earth is divided into these 4 layers. At least one way of looking at it is 4 layers. We have crust, mantle, outer core, inner core. We're going to ignore the 2 cores and only think about the crust and mantle. But what we do is we take the mantle and we split that into an upper and lower half. The upper half moves together with the crust, and that makes up a plate. Since those things are acting as one thing, we call that the lithosphere. The lower mantle we call the asthenosphere. Okay, so the last thing on here is the plates move in different ways. And I want you to describe in a real brief phrase each of these different kinds of boundaries. So you need to write down diverging boundary, converging boundary, transform boundary. The diverging boundary is where the magma comes up and the plates get carried apart. It's the rising portion of the convection current, and then the plates get dragged off to the sides. They're moving away from each other. They diverge. They go in opposite directions. At the end of class today, we will all diverge, go to a different place.
I have a question.
Good.
You said the rising point, and then what?
All you need to do for diverging boundary is say that the plates are moving apart.
Okay.
It happens where the convection current is rising. The hot magma is rising, and then it drags them apart. That's the important thing, because we live on the surface, right? So that's what impacts us, is that they're moving apart. But the reason they move apart is because of that rising magma spreading out right there. So diverging boundaries, the big idea is they move apart. Converging boundaries are the opposite. It's where they come together. And this is what we did at the beginning of class. We all converged here, right? So these 2 plates might slam into each other. One might get slid underneath another. They might crumple up. As we'll see, there are a couple different kinds of converging boundaries depending on what type of plate is involved. But the big idea, converging, comes together. And then the third type of boundary is called a transform boundary, and it's where the plates slide past each other. One is going in one way, one's going in another way. They're not moving apart. They're not colliding with one another. They're just opposite directions of traffic on the freeway, right? So that's what we mean by a transform boundary. Okay, so now we're going to start with our drawings. The first drawing, you should label it with a title at the top. It says types of crust. And you start by drawing these shapes, and then we're going to add some things to it. I'm going to draw with you. Let's start by drawing these shapes. This should probably fill your page. Like your paper should be about as wide as this drawing is. The edges of your paper might be over here and over here. So make this the full width of your page. So it might end up taking a half page total. And while you're drawing that, I want you to also think about, can you remember what the two types of crust are called? Do you remember what kind of rock they're made of? Do you remember which is thicker and which is thinner? And do you remember which one is denser? Which means when they collide, the denser one goes underneath the other one. So think about those things. Then I'm going to grab a blue pen here because I'm going to show the water of the ocean. Something like that. And so that should give you a pretty good hint that the plate on the left is what we call oceanic crust. Meanwhile, the plate on the right is called continental crust. The next thing to think about, oh, and you can see for sure, just by a glance, which one's thin and which one's thick, right? Now, when we're talking about oceanic crust, we're not talking about the water here. We're not counting the water. We're talking about the sea floor. And that's like 5 miles thick. This is like 50 miles thick. The next thing we're going to do is we're going to use these symbols that are normally used by geologists to represent different rock types. All right, so the first one's an easy one to draw. I'm going to use black for this. And that is the rock that makes up the sea floor. We just show with these vertical lines. So add that to your diagram. And then up here, I'm going to make a key showing what this is. And this is our symbol to represent rocks of the salt. So add that key on there. Next, we want to show the type of rock that makes up the continental crust. So I'm going to add it to the key first. And this is mostly granite. So basically, I think of this symbol as X's that did not quite cross. Or you could think of them as writing -1 a bunch of times at an angle. So I'll show you over here. See how that's kind of -1 over and over again? And then we do the opposite pattern on the other side of it. Fill up the space. Or you can think of it as 1 minus 1 minus 1 minus 1. But the idea is that they're at angles like you took an X apart. And we're just going to fill up this whole continent with this granite rock here. How about if you guys give me a thumbs up just on the comments when you've got that done, or you can show me your thumb. All right, thanks, Marisol. Thanks, Jessica. I think that's Rose. Something's happening. The background is kind of flashing around. All right, Noah, thank you. All right, next. A moment ago, I gave you these two new vocabulary terms of lithosphere and asthenosphere. In this diagram, we can see the entire lithosphere, the entire thickness of it. Remember, we're looking at the edge here. We've kind of cut into the Earth, and we're looking at it edge on now. We're not looking down on it. We're looking at the edge of it. And underground, we can see in this diagram all of the lithosphere and some of the asthenosphere. To show those, I'm going to use a dotted line, and I'm going to use red since they're magma. And I'm just going to bring a dotted line across here. We would have to zoom out further in order to see the core of the Earth at all. We can't see the outer core or the inner core. Only the lithosphere and part of the asthenosphere. That's all we can see. So remember, the lithosphere is going to include crust and upper mantle. So everything from the dotted line up is lithosphere. And that's the same thing over here. If I was to use the continental crust, this would still be lithosphere on this side. Everything from the dotted line downward until you hit the core is going to be asthenosphere. So I'm going to show this with a bracket, but I'm going to make the bottom of it be an arrow showing that it continues deeper. My writing is sloppy enough even without trying to do it on the screen here. If you can't read that, let me know. Asthenosphere. A-S-T-H-E-N-O sphere. I think I made it worse. Asthenosphere. And that is the lower mantle. So that means that this is the upper mantle above the dotted line. Below the dotted line is the lower mantle. Now, if you put those two together, we should end up with the mantle. So do you see how we've kind of taken the mantle and we've split it into an upper section and a lower section? The lower section is much thicker than the upper section. We just can't see it in this diagram because the mantle continues. Basically, if you were in my classroom, I would tell you that it continues to the floor. So in this diagram, the mantle would go all the way to the floor of my classroom. Okay, and when you are done with this diagram, give me a thumbs up so I know that we're ready to move on. All right, thanks, Gabe. Thanks, Jessica. All right, Rose. Thanks, Marvin. All right, Noah. You doing okay, Marisol? Okay, cool. So I'm going to erase all of this. This was only a comparison of the two kinds of crust, right? In a diagram format, but we're going to make another comparison as a chart. So I'm going to erase this. And then the next thing I'd like you to do on the same page, you can just do it underneath that one, is copy down this chart. So make a little table, a 2x4 table, 3x4, where we're going to make these 4 comparisons. Actually, it's a 3x5, isn't it? We're going to make these 4 comparisons of these 2 types of crust. Now, based on looking at our diagram, I'm going to ask Marisol to tell me what kind of rock is the ocean crust mostly made of? What kind of rock is the ocean crust made of, Marisol? It's on the diagram we just drew. Look at the key that we drew at the top. We wrote down
basalt rock?
Yeah, it's called basalt.
Basalt rock.
Basalt, yep. So the main rock type of the ocean crust is basalt. Good job. Rose, what about the main rock type of the continental crust?
Wait, what was it? The granite rock?
Exactly.
Ah.
And I really appreciate that you did not take that for granted. Okay, next, thickness. All you have to do is tell me which one's thinner and which one's thicker. Marvin. Oceanic crust, is it thin or thick?
It's thin.
There you go. And I'm going to write down actually how many kilometers it is. You don't have to memorize these numbers, so you don't even need to write down the numbers, okay? So the oceanic crust is thin. Gabe, what about the continental crust?
Very thick.
Yeah, it's about 10 times as thick, 5 to 10 times as thick. Just to put this in miles for you, the ocean crust is anywhere between 3 and 7 miles thick. So if you wanted to drill to the mantle and take a sample of magma directly from the mantle, you'd have to have a drill bit that was like 5 miles long to get there, plus the depth of the ocean that you were drilling through. On the other hand, continents would be even more difficult. They're like 50 miles thick. Hey, Noah, do you remember, because I've taught you this already, so I'm testing you, do you remember the density of ocean crust versus continental crust? You don't have to remember the numbers, but which one was more dense?
Oh, okay.
Which was less dense?
Yeah, I was like, I don't know the exact number, but I know oceanic crust is more dense because it slips under the continental crust when they converge.
That's exactly right. Good job. So once again, you don't need to memorize these numbers, just which one is more dense and which one is less dense. And if you notice both of them are greater than 1. And hopefully you remember that if it's greater than 1, then that means that it will sink in water, right? Does that make sense? And then Jessica, I don't know if you remember this at all or not, or just take a wild guess. Which do you think is older and which is younger, ocean or continental crust?
Is the ocean crust younger?
It's way younger, exactly. So it might not seem very young because the ocean crust, what's happening here, sorry. The ocean crust is still millions of years old, 200 million years old, at least at the oldest part of it. Now, new ocean crust is being made all the time at the mid-ocean ridge, but the older ocean crust is being destroyed all the time where it gets pushed underneath the continent. So all the oldest rocks of the ocean floor have been destroyed. So it's a relatively young 200 million years old. Now compare that to the continental crust, much, much older, 3.5 billion years old. So continental crust is over 1,000 times the age of the ocean crust. All right. Again, you don't have to write down any numbers on this page, just the comparisons, thin versus thick, high versus low, young versus old, and that's all you need to know. All right. So we're going to do one more diagram today. And actually, no, we're supposed to do 2 more diagrams today. Sorry. So what we're going to do is start with the diverging boundary, which is the one where they move apart. So you can start a new diagram. Again, you're going to want at least half a page for this. I might just flip my paper over and start on the back at this point because it's an obvious dividing line between one topic and another. And this diverging boundary is mostly found under the ocean. So I'm going to draw the sea, surface of the sea up here. Since it's diverging, we know it is moving apart. I've already told you that just by giving you the name diverging. So let's show these guys moving apart. Now, the reason they're moving apart and the reason you can see they've been lifted up, right? The rest of the crust, this actually continues off my screen for, let's see, you know where my classroom is. This would continue off my screen at least as far as the stairwell, if not all the way to the end of the building. So this is just the point where they are splitting apart. It's not the entire plate. And they've been lifted up right here to form an underwater mountain range. So at the top of the mountain range, you can see there's a split. This split is called the Rift Valley. A rift means a tear or a break or a split. So we call that the Rift Valley. This whole zone that's been lifted up, I'm going to show that up here with a bracket. Where it's been lifted up, this whole thing is called the Mid-Ocean Ridge. It's an underwater mountain range. And to show you a little more of a 3D view, I'm going to draw something else on here, but I don't want you to draw it. Okay, I'm going to draw it and then I'm going to erase it. But just to give you a more 3-dimensional view, this would extend off into the distance. And so would this side over here with this valley at the top. Right? So we have this valley at the top of a mountain range. And this keeps going off into the distance. Okay? You don't need to draw that on yours, though. I'm not sure we have a lot of things to add to this diagram, so I'm not sure you'd have room anyway. Just wanted to give you that visual. So I'm going to erase those things I just added. Okay, so why is it that they're moving apart? And why is it that there's a mountain range at the very location where they move apart? Well, anytime we're talking about plate tectonics, you can almost guarantee that the answer why will involve convection currents. That means we need to go down here into the lithosphere. And we need to show, first of all, magma is rising up right here, lifting this mountain range from the bottom of the sea floor. But the magma can only rise so far, so as a result, it has to spread out. And it's going to drag these plates along with it. So this is the rising part of a convection current. The convection current is coming up here on both sides. It's the rising part of a convection current. That rising magma lifts up the crust to make the mountain range, the mid-ocean ridge. But at the top of the ridge, it's splitting apart between the two plates. That means that magma can continue to rise up here, and we get new magma forming on the inside of the ridge. We get new rocks forming here as the magma hardens. When that molten rock hardens and solidifies, now it's known as this basalt rock. It's a volcanic rock that came from the magma, that came from the lava. So that occurs inside the Rift Valley. And we've actually taken submarines down to a Rift Valley and made underwater film of the magma bubbling up and hardening pretty quickly underwater because the water's so cold. It hardens fast. Now, we already talked about a couple other details here when I gave you evidence for plate tectonics. And that first detail we want to talk about is comparing the ages of the rock in the plates. So rock that is here, I'm going to label with a Y and an O over here. Same thing over here. I'm going to label this Y and O. Notice it's a mirror image, left to right versus right to left. Y means young. And O means old. So we see the youngest rocks are the closest rocks to the ridge. And that's because new magma here is forming. And then the new rock that just got formed gets dragged off to the side. And that means the longer it's been since it was formed, the further away it is. It's been dragged further away. And we see this mirror image here. Fresh rock is forming right now. This is baby rock. This is like infant rock. Here's preschool rock and kindergarten rock and third grade rock and so forth, right? The rock gets older as it gets spread further apart. It takes time for that to happen. And there's another way that we've confirmed this, and that is by analyzing the thickness of the sediments that build up on top of the plate. So over time, all kinds of things settle to the bottom of the ocean floor. Same thing is happening in the lake. Sand that gets carried by a creek ends up washed out into the lake. It settles down to the bottom of the lake. Same thing with silt and mud particles and bits of clay. In the ocean, it would also include bits of shell. Sea creatures that die sink down to the bottom. any of these particles of material we call sediments. And it takes time for them to build up. And as a result, we can see on the mid-ocean ridge that the ages of the sediments vary depending on location. So we're going to show the sediments with dots at the top of the plate. This is like the sand on top of the plate. But notice as I'm getting further from the ridge, I'm making this a thicker layer. The further I am from the Rift Valley, the thicker the layer of sediments. And we see this mirror image on the other side. It's thin next to the ridge, and then it starts building up more and more over time as the rocks have had more time to accumulate more of these particles that sink down to the bottom of the sea floor. All of these things combined suggest that the new magma is coming up from the mantle, being hardened into rock in the Rift Valley, and then it's ripped in half. And some of it is dragged to the left and some is dragged to the right. And we see that the age of the rocks shows this pattern. The thickness of the sediments shows this pattern. And most importantly, that we're not going to include in this diagram, the pattern of magnetism, ancient magnetism, paleomagnetism, shows this same thing too. Okay, and that's all we need for this diagram. So give me a thumb up when you're ready to move on. Thanks, Marisol. All right, thanks, Jessica. All right, Marvin and Noah, thank you. So this Rift Valley is kind of amazing. It's not only in the ocean. There are some continents that have a Rift Valley, and we think that the continent is being ripped in half right there, and that eventually, once that valley is torn long enough to reach the sea, it will fill with water and we'll have a brand new ocean being born. This is happening in Africa. And a little further along in the process is the Red Sea. The water has now filled that Rift Valley. Let's see. Gabe and Rose, can I erase this? Thanks. Okay, here we go. Moving on. So again, I'm going to give you a massive amount of information, and we're going to really reduce it down to a smaller amount that you need to remember, that you need to write down. We're going to watch a video in a moment. But first, let's have a look at some of the details of the Rift Valley. You're not going to write all of this down. I'll tell you what to write down. So basically, the first 5 bullets describe the process. So you don't need to write any of that down. But let's read through it together. The hot magma of a convection current rises and spreads out in opposite directions, dragging plates apart. The rising magma lifts the seafloor upward to make an underwater mountain range, the mid-ocean ridge. The mid-ocean ridge splits at the top, forming a rift valley. Some magma breaks through the rift and hardens into basalt rocks. This keeps happening, and the older rocks move off to the sides as the plates are pulled apart, allowing more young rocks to form in the Rift Valley. Okay, now this results in a process. I would like you to know the name of this process, which is seafloor spreading. Okay, so you should write down that seafloor spreading is the process that occurs at a diverging boundary. So if I ever ask you a question, what process occurs at a diverging boundary? You're looking for seafloor spreading. Let's do this. So one of the things you'll need to be able to do is tell me the process that occurs at each boundary. This is your answer for the diverging boundary, seafloor spreading. Next, you should be able to give me some examples of where each of these processes is happening. So what's an example of a diverging boundary? Well, this is a good one. Mid-Atlantic Ridge. I just mentioned the Red Sea also. That's another option. It's another example of a diverging boundary of seafloor spreading. And a third example that's in the very early stages is the Rift Valley, just starting to split apart. So here are three examples of where seafloor spreading is occurring. They're all diverging boundaries. I want you to write down one more thing, one more list, short list about seafloor spreading and diverging boundaries, and that would be features. Things that we find at a diverging boundary, the features we find. And maybe you remember that we saw a mid-ocean ridge there. We also see a rift valley at a diverging boundary. So those are the main features you should know about, the process that occurs, and examples. So for each of these boundaries, we'll be looking for those things. We'll be looking for features, we'll be looking for the process that occurs, and we'll be looking for examples. Okay, let's see if that video is ready yet. So this is going to be an animation of what's happening. So the idea here is that I just want to give you some action to help cement in your mind what we're talking about with diverging boundaries and seafloor spreading. So here we see the asthenosphere, the mantle rising up, the magma rising up through the mantle, and it reaches this rift valley and it hardens into rock. And here's some of that new magma. And then it gets dragged apart. The convection currents drag it off to the side. We have more new lava being hardened into new rock. And notice that the new rock gets split apart and it gets dragged to the left and to the right. And so the oldest rock is furthest from the ridge. The newest rock is in the middle of the Rift Valley, just forming just now. But then it gets split apart and dragged again, huh? Okay, so here's another really nice diagram of this, I think, almost a piece of art. It's showing the same thing where we have the asthenosphere down here in the dark red and the dark orange. And the lithosphere includes the upper mantle along with the crust. We have the magma rises up. And then it spreads out to the sides, huh? Where it's rising up, we have this underwater mountain range, a mid-ocean ridge. And the top of the mid-ocean ridge splits apart, and we can zoom in on it here. So we're going to zoom in on the Rift Valley. Here we are zoomed in, and notice it's pretty jagged looking rock inside the walls of the Rift Valley, isn't it? And we can see where the magma is coming up and forming new rock. And of course, as magma is forcing its way through rock, we're going to have earthquakes. But they're not very deep underground, and that's why they call them shallow focus earthquakes. The focus is where an earthquake begins. So of course, if this whole crust is moving and magma is forcing its way through there, there are going to be earthquakes there, right? Now, what I really like about this diagram is the way it's kind of 3D. So we can see off in the distance here, that this mid-ocean ridge continues into the distance. Although it's not a perfectly straight line, it's broken apart into segments. And each segment is known as a spreading ridge or a spreading center. And they are joined by earthquake faults that move from side to side, known as transform faults. Nice image of a diverging boundary. Okay, this one's going to be quicker. There's less to write about a converging boundary. So go ahead and get this one set up. Once again, about half a page in size. Now with converging boundaries, different things happen depending on what type of plate is crashing into the other plate. This is what happens in this diagram when one continent crashes into another continent. But different things happen where a continent collides with an oceanic plate. And when two oceanic plates collide, it's actually quite similar to when a continent and ocean floor run into each other. So we don't have to do 3 of these converging boundaries, but we do need to do 2 of them. We're going to do one today, and we'll do one on Friday. Okay, now since these are continents, these are both granite rocks, and maybe you remember that our symbol for granite was almost an X, but not quite overlapping, or maybe it was a bunch of negative ones. This is showing the crystals. It's supposed to represent the crystals that we can see in granite. You know how granite has that speckled appearance. Both of these are granite, so we're going to continue this same pattern on both of them. Next, since these are converging boundaries, we know that they're coming together. So I'm going to put a big arrow showing that we have one continent crashing into another continent. All right, these continents are crashing into each other. And the reason they're crashing into each other, of course, why are they colliding? Like I said, if you hear that question with plate tectonics, your answer is going to be convection currents are bringing them together. So we have convection currents coming up here and then crashing into each other. This is where the magma has cooled off and is sinking again. So we have two convection cells side by side. And where they come together, they drag the plates together. And in this case, the continents crashed into each other and they crumpled up to form this mountain range. Imagine taking two pieces of carpet or two towels on a smooth floor and sliding them together. Wouldn't they crumple up where they collided? And that's the same thing that's happened here. You can see that where they meet, it's much thicker than off to the sides. So this is the thickest place of the crust, would be underneath one of these mountain ranges. Now, maybe you're thinking to yourself, well, if these continents are colliding, if they're crashing into each other, isn't that going to shake up the land? In other words, aren't there going to be earthquakes? And the answer is yes, there are. So we're going to symbolize earthquakes with an asterisk, a star. And then we're going to put them along this border on both sides of it. Some are shallow and some are deep. We can actually follow the, we can measure the boundary between two continents by plotting the locations of earthquakes that occur. One of these earthquakes occurred maybe 5 years ago. It was a major earthquake in Nepal in the Himalayan mountains and did a lot of damage and killed people. Terrible. And actually, we only need to put one more thing on this diagram. I'm going to use green just so it shows up. Now, imagine when two cars crash into each other, don't they end up bending the metal of each car? Doesn't the metal end up all crumpled where they hit one another? The same thing actually happens with the rocks that make up these continents. The rocks get folded, they get bent, they get cracked. So we're going to symbolize that with a wave-like symbol where the layers of rock have been bent, they've been folded. And so we're going to see these folded rocks. Again, it's going to be mostly along the boundary, right along the edge. You get these folded rocks. Not only that, this entire thing, this entire mountain range, let me redo that, it's hard to see. This entire mountain range is considered a folded mountain range. You could see lots of places where the layers of rock were all wavy. Giant waves as big as a building in some of these rocks, in these folded mountains. Now, not every mountain range is a folded mountain range. Where we live here in the Sierras, it is not a folded mountain range. We have what's called a fault block mountain range. So here's my demo for that. Perhaps you saw me show you this before. These little blocks are representing blocks of land, and the gaps between them are earthquake faults. And over time, as earthquakes happen, we see the center block drop lower and lower, while the outer blocks are rising higher and higher, forming two mountain ranges with a basin or a valley in the middle. This is a different way to form a mountain range, and this is the mountain range that we live in. In fact, the basin could end up being filled with water, and that's what formed Lake Tahoe. Meanwhile, we're living on the edges. We're like on this block right here, this fault block that has risen up to form the mountains where we live. In fact, this process still continues today. A couple years ago, they measured that Slide Mountain had risen by a foot during the year. Not all at once. That would have been a huge earthquake to lift the mountain all at once. But by lots of little earthquakes that we didn't even feel, it lifted Slide Mountain 1 foot higher. Now, of course, at the same time that the mountains are rising, they're also being eroded away. So there's this battle. There's a balance in mountains between erosion and uplift. One builds it up higher, the uplift, the other erodes it away lower and lower. And we can see this especially in an old mountain range. In an old mountain range that no longer has these forces of uplift, like the Appalachians in eastern United States, those mountains are not very tall, and they're also pretty smooth because they've been so eroded. If I'm okay to move on, give me a quick thumb up. All right, so I'm going to erase this. And we're going to look at another video. And we're going to write down a couple things about the colliding continents. And then we'll be done for the day. Okay, so the best example of one continent crashing into another is the Himalaya Mountains in Asia, the tallest mountain range in the world. So the story starts with Pangaea breaking apart, and what I really want you to look at is India right here. Look at India heading north. India's moving north, and it's headed towards Asia. It's going to collide with Asia, one continent crashing into another. When it hits, it's going to push up this massive mountain range. It's not only the tallest in the world, but it's very thick. And that is Mount Everest, the highest mountain on the planet, something like 25,000 feet. You'd have to put Mount Rose on top of Mount Rose, and that's from the ocean, not from just Tahoe, to even approach the height of Mount Everest. It's huge. The air is so thin up there that you can't live very long because you don't get enough oxygen. They call it the death zone once you get above maybe 20,000 feet. Most people that climb it bring oxygen with them. Okay, so let's look at this and we'll figure out some things to write down. Remember, we're looking for features, we're looking for the process, and we're looking for examples, right? We're looking for those three things. In fact, you could write those three things on your paper right now, because we want to find features of colliding continents. We want to find the process that occurs. And we want to find examples of where this is happening. So we're looking for these three things. All right, here we go. Convection currents in the asthenosphere carry two continental plates together. The collision causes the plates to crumple up, forming folded mountain ranges. Earthquakes occur as the rocks are smashed together. An example is the Himalaya Mountains, formed where India crashed into Asia. The only thing missing there is the process, which I would call mountain building. Or even better, if we pointed out that it's folded mountain building.
Wait, what do we put for, oh, never mind.
All right. And that's all I have for you today. Let me see. We actually have another 20 minutes of class. I do not have a new assignment for you to do, but I would like you to spend this 20 minutes making up any missing work. All right? So go back to old assignments and make those up. I'd like to point out two things first before I release you. Just a couple of logistical things. First, I now want you to do two things with assignments when you finish them. I want you to put the assignment in the usual place with the assignments, but I also want you to put it in your notebook right away. You were going to do both of these anyway. I just want you to do them both right away. The reason for that is when you put it in the assignments, it notifies me that you have an assignment, but I can't grade it there. However, when you put it in the notebook, I can grade it, but for some strange reason, I don't get a notification that you added it to it. It'd be great if Teams was giving me a notification and allowed me to grade it in the same place, but it doesn't. So I need to ask you to do those two things every time you finish something. The second announcement I have for you is there is a possibility that we have a delayed start tomorrow. But wait a minute, guess what? When we're distance learning like this, we don't have delayed starts at the high school, as we learned on Monday morning, right? So if there's a delayed start for the elementary school, we still have normal class. Now, if we were coming to the classroom, we would have a delayed start. But since it's all distance learning, we don't have to worry about it. So if they call a delay for the elementary school, we still begin at 7:30. Okay? That is different if they cancel school. If they cancel school, it's canceled for everybody, right? We don't have any distance learning on a snow day. It's a true snow day. Got it? Okay. And that's all I have for you. I would like you to spend the next 20 minutes working on makeup work, okay? And that's all I have. Thanks for being here.
Thanks,
Thank you.
All right.
All right, guys. Have a good one. Talk to you Friday.
You too. Bye.
Bye.
Thank you. Bye.
Bye.
Bye. Bye.